Counting shortcuts, chapters 3 and 4. We're going to use counting shortcuts to compute probabilities, especially for the binomial random variable. Example 1, a hiking club has 4 members. How many ways are there to choose a president, vice president, secretary, and treasurer? Answer, there are 4 choices for president. Once the president has been chosen, there are 3 choices left for vice president. After the president and vice president have been chosen, then 2 choices left for secretary. After the president, vice president, and secretary have been chosen, there's 1 choice left for treasurer. So altogether, there's 4 times 3 times 2 times 1, or 24 ways of choosing the 4 officers. 4 times 3 is 12, times 2 is 24, times 1 is 24. There's a notation for this expression here, 4 times 3 times 2 times 1. It's 4 with an exclamation point afterward, and it's read 4 factorial. If you want to compute 5 factorial, it's the same principle. It's 5 times 4 times 3 times 2 times 1. So you can multiply these in any order. 5 times 4 is 20. 3 times 2 is 6. 20 times 6 is 120, and then times 1 is still 120. 1 factorial is just 1, as you might expect. 0 factorial has a special definition. That's equal to 1. It's a special definition that makes some of the other formulas work that we'll be working with. So generally, it's n factorial is n times n minus 1 times n minus 2, and until you get down to 1. Okay. Okay, example 3. The hiking club now has 10 members. How many ways are there to choose a president, vice president, secretary, and treasurer? Well, there's 10 choices for president. After the president has been chosen, there are 9 choices left for vice president. After the president and vice president have been chosen, there's 8 choices left for secretary. After the president, vice president, and secretary have been chosen, there's 7 choices left for treasurer. So altogether, there's 10 times 9 times 8 times 7. So 10 times. So you can multiply these in any order. 10 times 9 is 90. 8 times 7 is 56. And then 56, 6 times 0 is 0. 6 times 9 is 54. Carry the 5. 5 times 9 is 45. And 5 is 50. So anyway, multiply these. You get 5,040 ways of choosing the 4 officers. And we also have a special notation for this. It's 10p4. You can read that as 10 permute 4. There's also a formula for this. N permute k, npk, is n factorial over n minus k factorial. So for example, if we want to compute a permute 3, that's equal to 8 factorial over 8 minus 3 factorial. 8 minus 3 is 5, so it's 8 factorial over 5 factorial. Well, 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Wait, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 on down will cancel. So we're just left with 8 times 7 times 6. 8 times 7 times 6. Well, 8 times 7 is 56. And then 56 times 6. 6 times 6 is 36. Carry the 3. 5 times 6 is 30. And 3 is 33. So there's 336. Well, the answer here was 336. Okay. So that's permutations. Okay, so example 5. The hiking club still has 10 members. How many ways are there to choose a 4-person committee? So this is a little bit different from choosing 4 officers, because when you choose 4 authors, for example, Ann being president and Bob being vice president is different than Bob being president and Ann being vice president. So it's, but for a committee, if Ann and Bob are on the committee, that's the same as Bob and Ann being on the committee. So for a committee, you could say the order, in a sense, the order doesn't matter. And so so there's so if we can start out the same way, we have 10 choices for the first committee member, 9 choices for the second committee member, 8 choices for the third committee member, 7 choices left for the fourth committee member, 10 times 9 times 8 times 7, 5,040 ways of choosing. But these include some double counting. So they include Ann and Bob, and as being a different committee than Bob and Ann. So what we wanted to eliminate the double counting here by dividing by the number of ways there are of rearranging the committee. So there's 4 times 3 times 2 times 1 ways of rearranging the committee. So if we divide by 24, we get 210 ways of choosing a 4-person committee. And the notation here, it's a little bit like a fraction here, 10 over 4, except there's no fraction bar and they have parentheses around it. It's also written 10C4, and you can read this as 10 choose 4. And the formula is for n choose k, n factorial over k factorial times n minus k factorial. So, for example, if we want to keep 8 choose 3, this is going to be 8 factorial over 3 factorial times 8 minus 3 factorial. Well, 8 minus 3 is 5, so this is 8 factorial over 3 factorial times 5 factorial. And then we can write out the factorials: 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. Okay, so 5 on down will cancel. And also the 3 and the 2 will cancel with 6. 3 times 2 is 6. So we can cancel these with the 6. And that leaves us with 8 times 7, which is equal to 56. So the answer there is 56. Okay. During a flu epidemic, 30% of children get the flu. In a random sample of 10 children, what is the probability exactly 4 get the flu? So we can use, this is, later we'll get into random variables. This is actually a binomial random variable, but for now I'm just going to use it as an example of using a way of using counting shortcuts. A full tree would have over 1,000 paths, and so it's not going to be practical to make the full tree. What we want to do is make a sample path where 4 get the flu. So one way that 4 can get the flu is the first 4 get the flu and the last 6 do not get the flu. Okay, that's one sample path. So for that path, the probability of that sequence here is flu, 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 not, 0.3 times 0.3 times 0.3 times 0.3, which is 0.3 to the 4th power, and then times 0.7 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7, which is 0.7 to the 6th power. If we multiply these out, we get 0.000952957. And then we want to count the number of paths where 4 get the flu. Well, this is one path, but it might be that the first 2 get the flu, and then 2 don't get the flu, and then maybe another 2 get the flu, and then 4 don't get the flu or something. There's lots of different paths where we'll have these same probabilities, and we'll have the same numbers getting the flu. The order doesn't matter multiplication, so the probability of each of these paths is going to be the same, but we just need to count the number of paths. That's going to be 10 choose 4, which we already computed back here, 10 choose 4 was 210. That we computed that before. So that was so it's going to be 210 times this path here. So the probability that 4 of the 10 get the flu is going to be 0.200120949, or approximately 0.2. So that's basically how the main place that we'll be using these counting shortcuts is with binomial random variable, which we'll get more into later. Okay, so some more examples of counting shortcuts. You'll see some problems like this in WebAssign. I like, the example with the flu is how it's actually used in practice. Here is more like it's just sort of an exercise, but it's something that you may encounter in WebAssign, so I want to go over it. How many ways are there to arrange the letters in the word mathematics? Well, two of the letters, we have two M's here, and we have a choice of 11 places where we can put the two M's. So we want 11 choose 2, and we can compute that either by hand or with a calculator, but it comes out to be 55 choices of where to put the M's. And then once we've chosen this location for the M's, then there's 9 letters left, 9 spaces left, and 2 of the remaining letters are A rather. We have an A here and an A there, and we have 9 choose 2. Once we've located the M's, we have 9 choose 2 ways of choices of where to put the A's. So again, we can work this out. 9 choose 2 is maybe I'll work both of these out. I'll do these. I don't really have room on this page, but let's get another sheet of paper here. So 11 choose 2 is 11 factorial over 2 factorial times 11 minus 2 factorial. It's 11 factorial over 2 factorial times 9 factorial. And that's going to be 11 times 10 times 9 times 8 times 7 times 6 times 5, 4 times 3 times 2 times 1 over 2 times 1 times 9 times 2 times 9 times 8 rather, 7 times 6 times 5 times 4 times 3, 2 times 1. Well, 9 on down was going to cancel. And 2 into 10 goes 5 times. So, and then what's left is 11 times 5. So it's 11 times 5, which is equal to 55. Okay, so that's where we got the 55 from. 9 choose 2. 9 choose 2. That's going to be 9 times 8 times 7 times 6. Oh, actually, before I do that, 9 factorial over 2 factorial times 9 minus 2 factorial. 9 factorial over 2 factorial times 7 factorial. 9 times 8 times 7 times 6 times 5, 4 times 3 times 2 times 1 over 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 on down will cancel. 2 into 8 goes 4 times. What's left is 9 times 4, which is 36. Okay, that's 9 choose 2. And then we do 7 choose 2. That's 7 factorial over 2 factorial times 7 minus 2 factorial. 7 factorial over 2 factorial times 5 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 5 times 4, 3 times 2 times 1. 5 on down cancels. And 2 into 6 goes 3 times. And so what's left is 7 times 3, which is 21. So 7 choose 2 is going to be 21. Okay, so once we've chosen the M's, and A's, and T's, those were the duplicate letters, the M's, the A's, and T's. Once we take those out, there's 1, 2, 3, 4, 5. Oh, there's only 5 letters left. So if we make H the next one, we have 5 choose 1 choices of where to put the H. So 5 choose 1. Five factorial over 1 factorial times 5 minus 1 factorial. 5 factorial over 1 factorial times 4 factorial. 5 times 4 times 3 times 2 times 1 over 1 times 4 times 3, 2 times 1. 4 on down will cancel. And we'll just have 5 divided by 1, which is 5. So 5 choose 1 is equal to 5. Once we've chosen the M's, A's, T's, and H's, I'll pick E next. I'm taking these in order from left to right, but you can choose them in any order. But we'll have 4 choose 1 choices of where to put the E. So 4 choose 1, it comes out to be 4. 3 choose 1 comes out to be 3. 2 choose 1 is 2. 1 choose 1 is 1. So altogether, we'll multiply these all together. 55 times 36 times 21 times 5 times 4 times 3 times 2 times 1. And it comes out to be 4,989,600. So that's a lot of different ways of rearranging those letters. Okay, next example, using a 26-letter lowercase alphabet to write secret codes, how many different 4-letter combinations are there? For example, AABA, ABAA, CDFZ, XUDF. So this includes duplicate letters. So we have 26 choices for the first letter. And after we've chosen the first letter, we still have 26 choices left for the second letter because we're allowing duplication, and then 26 choices for the third letter, and so forth. So it's going to be 26 times 26 times 26 times 26, or 26 to the 4th power, 456,976. Part B, how many different 4-letter combinations are there with no duplicates? For example, the word spot, each letter occurs only once. There's only one S, only one P, only one O, only one T. Same with pots, A, B, X, T, there's only one A, only one B, only one X, only one T, and so forth. So there's no, each word has no duplicates. And part A, we were allowing duplicates. So this is going to be 26 permute 4, because the order still matters. So spot, we're going to count spot is different than pots. They have the same letters, but in different order. So this is going to be permutations rather than combinations. So it's 26 P4. So if we compute that, get another piece of paper here. 26p4 is 26 factorial over 26 minus 4 factorial. So that's going to be 26 factorial over 22 factorial. So I'm not going to write all these out. Let's just put etc. So 26 times 25 times 24 times 23 times 22 times 21 times 20, etc., all the way down to 1. And 22 factorial, 22 times 21 times 20, etc., all the way down to 1. So 22 on down will cancel, and we're just left with 26 times 25 times 24 times 23. So you can also so that's expressed in terms of permutations. You can also think of it even without doing permutations. There's 26 choices for the first letter because we're now allowing duplicates. Then there's once the first letter has been chosen, there's 25 choices left for the second letter, and then once the second letter has been chosen, 24 choices left for the third letter. Once the first 3 letters are chosen, then 23 choices left for the fourth letter. So it's 26 times 25 times 24 times 23, or 358,800. Okay, so part C, how many different ways are there to rearrange the same 4 different letters? For example, spot, pots, tops, stop, post, ops, all have the same 4 letters, but in different order. So if you're just looking at, once you've picked the 4 letters, 4 different letters, you have 4 choices for where to put the first letter, times 3 choices where to put the second letter, and so forth. 4 times 3 times 2 times 1 is 4, or 4 factorial. 4 times 3 times 2 times 1 is 24, so, and that's also equal to 4 factorial. And then part D, how many ways are there to choose 4 different letters if the order doesn't matter? So we already computed the number of different 4-letter combinations where the order does matter, and if we divide by the number of ways of rearranging these 4 letters, then we'll get this is equal to we've computed this up here is 358,800, and the 4 times 3 times 2 times 1 is 24. And then divide, you get 14,950. And that could be also written as 26 choose 4. So we could, if we do 26 choose 4, I'll do that on a separate page. 26 choose 4, 26 factorial over 4 factorial times 26 minus 4 factorial. Is 26 times 25 times 24. Well, this is, before I do that, 26 minus 4 is 22. So 26 factorial over 4 factorial times 22 factorial. 26 factorial, 26 times 25 times 24 times 23 times 22 times 21 times 20, etc., all the way down to 1. 4 factorial is 4 times 3 times 2 times 1. 22 factorial, 22 times 21 times 20, etc., all the way down to 1. So 22 on down cancels. If you want, you could cancel the 24 with the 4 times 3 times 2, or you could just multiply them out. 4 times 3 is 12, times 2 is 24, so they'll cancel with the 24 there. So we're left with 26 times 25 times 23. And if you multiply those out, you should get 14,950. Let me just double check on the calculator here. 26 times 25 times 23. Yeah, 14,950. Okay, well, so that concludes this presentation.